Right now, at this exact second, there are 2 points on directly opposite sides of the Earth that share the exact same temperature and barometric pressure. This meteorological guarantee is a strict geometric necessity, an inescapable property of continuous maps on a sphere. To understand why this must be true, we turn to the definitive text on the subject, James R. Munkres Topology. Specifically, we are going to look at 2 concepts from Chapter 9, Section 57, covering the Borsuk-Ulam Theorem, and Section 58 on deformation retracts. Munkres relies on rigorous algebraic logic to make his points. Our objective today is to translate those dense, written proofs into clear visual intuition. This diagram from the preface shows exactly why Chapter 9 matters. These sections map out the dependency pathways for the rest of algebraic topology. Moving from observable physical phenomena to absolute geometric guarantees reveals the core power of algebraic topology, proving what must be true for all continuous spaces. We start with S2, the standard 3-dimensional sphere. Points diametrically opposite each other, connected by a line through the origin, are antipodal points, labeled x and negative x. Consider a continuous map F, taking points from the sphere and plotting them onto a flat 2-dimensional plane. The requirement that F is continuous means points sitting next to each other on the sphere must land next to each other on the flat plane. We cannot tear or puncture the surface. This continuity constraint prevents us from arbitrarily scattering the sphere's points. It forces a predictable, unbroken mapping behavior. The Borsuk-Ulam theorem dictates that for a continuous map F, there must exist a point x where f of x equals f of negative x. Visually, squashing the sphere onto the plane forces at least one pair of opposites to collide on the exact same coordinate. Munkres proves this using a subtraction helper function. G of x equals f of x minus f of negative x. Under this framing, if mapped points are equal, subtracting them yields 0. Our objective shifts. We are hunting for the origin point. The proof proceeds by contradiction. We assume g of x never hits 0. If that were true, we could project the entire sphere onto the lower dimensional boundary circle, Sn-1, without ever intersecting the origin. Munkres demonstrates that such a projection is impossible because of the fundamental group. On the 2-sphere, every loop can be continuously shrunk to a single point. On a 1-sphere, the circle, there are loops that cannot be shrunk. Because these algebraic properties don't match, the mapping cannot exist, and the assumption fails. These dimensional constraints mathematically enforce absolute symmetry. You cannot compress a higher dimensional space into a lower one without folding at least one pair of opposites perfectly onto each other. While Borsuk-Ulam details rigid geometric constraints, Section 58 explores flexibility. We need a way to classify topological spaces that look entirely different but share identical underlying structures. We use homotopy, a family of continuous maps morphing one function into another, defined as h. The unit interval represents continuous time, parameter t. At t equals 0, we have our initial function, a tangled loop, f sub 0. Progressing t forward, the map untangles, smoothly transforming into our final function, a perfect circle, f sub 1, at t equals 1. Homotopy provides a rigorous and quantifiable mathematical framework. It allows us to declare 2 distinct shapes as structurally equivalent without ever breaking the rules of continuity. A deformation retract is a specific type of homotopy, taking a bulky space and continuously shrinking it into a nested subspace. At t equals 0, the mapping is the identity function. The thick volume remains untouched. As time moves to t equals 1, every point gets continuously pushed inward until the entire space is squashed into the thin, one-dimensional wireframe, subspace A. The critical constraint here is that the points already sitting on the wireframe do not move at any point during the deformation. The payoff for this shrinking maneuver is precise. If a larger space can deformation retract onto a subspace, their fundamental groups are perfectly isomorphic. Calculating the algebra of a complex solid volume is difficult. Retracting it to a simple wireframe makes calculation simple, because the algebraic answers are identical. Deformation retracts operate as topological X-rays. They let us strip away the superficial spatial volume and directly compute the structural rules governing the space. Placing these concepts side by side reveals the broader objective of Chapter 9. Borsuk-Ulam proves that when higher dimensional spaces map to lower ones, they contain absolute, unavoidable symmetries. Deformation retracts prove we can pare down complex spaces to their absolute foundational essence without losing mathematical truth. Algebraic topology bridges the physical geometry we can visualize with the rigorous algebra we can compute. Internalizing the geometric intuition behind these proofs allows us to recognize the algebraic invariants that dictate the behavior of any continuous space. For those ready to continue building that intuition and tackling higher-level mathematics, subscribe and join us for the next chapter.